Welcome. So I'm making this video to give more clarity on Prim's algorithm. See, previously we have discussed Prim's algorithm, uh, but if you look it at that way, it may not work for all cases and for all graphs. So I want to give more clarity on that. So previously we discussed that we will start with vertex 0, I mean the root vertex, identify the minimum cost edge, add it to the graph, then go to the other end of the edge which is added. From there you identify the minimum cost edge and add it to the graph, so on and so forth until n minus 1 edges are added. Okay, so this is the case which we have discussed, but that may not work with all the graphs. For example, to take this particular graph, if you apply that way, what will happen in the sense, let us say 0 is the root vertex. From 0 there are two edges, one with a cost of 10, another one with a cost of 7. So we will pick up this path and we will add this edge. Now we have to identify from vertex 2 what are the minimum cost edge. The minimum cost edge is 9. There are three edges, 32, 23 and 9. So we will take this edge. Okay, so this edge is leading to, this is edge 2 to 1. So from 1 next we will identify which is the minimum cost edge. So from 1 there are three edges, 9, 10, one with a cost of 9, another one with a cost of 10, another one with a cost of 5. So this 5 is the minimum cost edge, so we will take this path. Now if you see from 5 which is the minimum cost edge, already this one is added, so we cannot take this. Here there is no other edge, so the algorithm will stuck here. The algorithm will stuck here, it will never identify these edges. So this is the problem with that particular approach. So now let us discuss this with more clarity, how it actually works for all the cases. Okay, so that's the objective of this video. Okay, so let me briefly explain the algorithm. So we will be maintaining two lists. Okay, one is called as the vertex which were visited. Okay, vertex visited. The vertex visited will be, initially itself it will have one vertex which is 0, or the root vertex. So first itself we assume that the root vertex, before the algorithm start itself we assume that the root vertex is visited, because we are going to start with root vertex. And next is edges visited. Edges visited will be initially empty, nothing, no edges were initially visited. So algorithm starts with the root vertex. From root vertex you identify the minimum cost edge and add it to the edges visited. So which is the minimum cost edge? 0 to 5 is the minimum cost edge. So just add it to the edges visited list. So now we have visited one more vertex also, that is 5. Add this vertex 5. So this is what at the end of first round. Now for the second round we have to identify such an edge from the graph. We have to identify such an edge from a graph. Edge is nothing but edge we can represent like this, E1 comma E2, where E1 is the starting vertex and E2 is the ending vertex. Okay, or let me say, okay, let it be E1 comma E2. E1 is the starting vertex and E2 is the ending vertex. So now we have to identify such an edge from the graph such a way that E1 is already in the tree. E1 is already in the spanning tree, but E2 is not in the spanning tree, and that should be a, and also we have identified such an edge which is a minimum cost edge. Okay, so currently how many vertices are in the tree? 0 and 5. These are the two vertices. So this is the only edge we have added, 0, 5. So we have only two vertices, 0 and 5. So we have to identify such an edge such a way that E1 is in the tree. The starting vertex is in the tree, but the ending vertex is not in the tree. Okay, so there are two vertex. So from 0 you see, 0 to 5 if you see both edges are in the tree, so we cannot take this. 0 to 1, this is one option we have. Okay, similarly from 1, other way around if you see, okay, from E2 also we can see. Okay, from 5 also we can see. That is, one of the vertices should be in the tree and the other one should not be in the tree. So from 5 also we can see 5 to 0 is already there, 5 to 4 is not there. Okay, I think this is clear. This is the one which we have to understand clearly. That is what edge we have to add in the sense, or instead of calling E1 and E2, if it is confusing, I will call it as what you call small v, V1 and V2. Okay, let us assume this is capital V, VV, vertex visited, this is capital V. Okay, both are capital V, right? Whereas here I am talking about small v, V1 comma, we have to identify an edge V1 comma V2 such a way that V1 is visited and V2 is not visited. Okay. So now already visited category we have how many vertices? 0 and 5. So we have to identify an edge which is arising either from 0 or from 5, but ending should not be either 0 or 5. Okay, right? So from 0 we have only one option, that is 0 to 1. From 5 also we have only one option, that is 5 to 4. So which edge we can add? 5 to 4 only we can add. From this we have to pick up the minimum edge and which will not create a cycle. So add 5 to 4 to the edge list. Okay. Now we have visited one more vertex, that is 4. Okay. Now this is the end of second iteration. Now from these 3 vertices we have to identify an edge such a way that starting vertex is visited and ending vertex is not visited. So now we have 3 vertex to check, 0, 5 and 4. So from 0 if you see we have one option, 0 to 1. From 5 if you see we have no option because 5 to 4 is also now added to the spanning tree. 5 to 4 also now added to the spanning tree. So now from 0 we have one option, 0 to 1. From 5 we don't have any option. From 4 if you see we have many options. We have 4 to 6, we have 4 to 3, we have 2 options, we have 4 to 5 is already added. Okay, so from these 3 pick up the minimum cost edge. Which is the minimum cost edge? 28, 24, 22. This 4 to 3 is the minimum cost edge. So add this 4 to 3, we will add it to the edges visited list. 4 to 3. So this edge is added. So now one more vertex we have visited. One more vertex we have visited. So this is the end of third round. Now we have to, from all these 4 vertices, we have to identify such an edge V1 comma V2 such a way that V1 is visited and V2 is not visited. Okay. So again, if you start from 0 we have only one option, that is 0 to 1. From 0 we have only one option, 0 to 1. From 5 we don't have any option, all the edges were added. From 4 we have one option, I think. From 4 if you see 4 to 5 is added, 4 to 3 is added. So we have one option which is nothing but 4 to 6. 4 to 6. From 3 if you see why 4 to 6 means because 4 is added, 6 is not added. From 3 if you see 3 to 4 we cannot take because 3 is also added, 4 is also added already in the visited list. Okay. So we have only what? 3 to 6 we have one option. 3 to 2 we have another option. So out of this 4 which is the minimum cost edge, 3 to 2 is the minimum cost edge. So we will add this 3 comma 3 to 2. So now we got one more vertex which is visited. This is the end of fourth round. Now from all these 5 vertices 2, 3, 4, 5 and 0, we have to identify an edge such a way that V1 is already in the tree and V2 is not in the tree. Okay. So again if you repeat this process, again what we will get for 0 we have this 0 to 1, this edge still it is available, one option. There is no edge from 5 because 5 0 if you see both were already visited. 5 4 is already visited. Okay. 4 to 5, 4 and 5 both were in the vertex list already. 4 and 6, 4 is in the vertex list, 6 is not in the vertex list. So V1 should be in the vertex list and V2 should not be in the vertex list. So 4 to 6 we have one option. 4 to 3 we cannot take because 4 is in the list, 3 is also in the list. Next 3 to 6, next from 3, vertex 3 if you see 3 and 4 both are in the list, so we cannot take. 3 and 6 we can take. 3 and 2 we cannot take because 3 is also in the list, 2 is also in the list. Then from 2 if you see 2 to 3 we cannot take because 2 is also in the vertex list, 3 is also in the vertex list. This is 2, this is 2. Okay. Next 2 to 1 if you see 2 is in the list, 1 is not in the list. So this we can consider. So these are the 4 options we have. Out of these 4, which is the minimum cost edge? 2 to 1 is the minimum cost edge with the cost of 16. So this we will take 2 to 1. So if you add 2 to 1, so now we got one more vertex, that is 1. Okay, this is at the end of 5th round. So now from all these 6 vertices, we have to identify an edge such a way that one of the edges in the first starting edge is in the tree and the ending edge is not in the tree, and also it should not create a cycle. Okay, and also it should be a minimum cost edge. So again, if you start with 0, we have this option 0 to 1, and 5 there is nothing. 4 to 5 added, 4 and 5 both are in the vertex list, 4 and 6 is not, so still we have this option. 4 and 3 both are in the vertex list, so we cannot. Then from 3 to 4 both are in the vertex list, 3 and 6 is not in the vertex list, so 3 to 6 we have this option. 3 to 2, 3 and 2 both are in the vertex list, so we cannot take this. From 2 if you see 2 and 3 both are in the vertex list, so no. 2 and 1 both are in the vertex list, no. Okay, from 1 if you see 1 to 6 is one option, 1 to 0 is nothing but 0 to 1, which is already we are considering. So these are the 4 edges. Out of these 4, the minimum cost edge is 1 to 6 at the cost of 14. So this is the one we will consider, 1 to 6. So now we are adding one more vertex, that is 6. Okay, but now if you see how many edges already added, 1 2 3 4 5 6, and the graph contains how many vertices? 7. So already 6 vertices added. It means the spanning tree is 2 to 1 already added, now 1 to 6 you added, which means the spanning tree is formed. So you can terminate the algorithm. Otherwise there is another way also to terminate. Otherwise if you just continue also, now if you continue, what we have to identify? We have to identify from all these vertex, that is from all the 7 vertex, we have to identify an edge such a way that starting vertex is visited, ending is not visited. Okay, and also it should not create a cycle. So actually you will not be able to find such an edge. So that is also one of the way to terminate the algorithm. For example, 0 to 1 we have this option. From 0 we have only this option. From 5, now all vertex were added. So from 5 you cannot identify. Actually from 0 also, now if you see what is the condition, from 0 also you cannot identify any vertex. Okay. In the previous round also, actually from 0 we cannot identify. We should have ignored that. Because what? Because what is the rule says? The rule says one of the vertex, starting vertex should be added and ending should not be in the tree. Okay. So now all vertex were added. So you cannot identify any edge which is not added. So actually in the next iteration it will not identify any edge. So if the algorithm is unable to identify any edge, then also you can terminate. Okay. So this is the condition for terminating Prim's algorithm. Okay, so here is the algorithm. So T represents the set of edges. Here T represents the set of edges that were already added to the spanning tree. Initially it is empty. Where TV represents the set of vertex which is visited. T represents the set of edges which is added, which is initially empty. TV represents the set of vertices that is visited. Initially it is root vertex, 0. 0 represents root vertex. Okay. So while T contains fewer than n minus 1 edges, as long as this T contains less than n minus 1 edges, do this. What you should do? Identify an edge u comma v. Identify an edge u comma v, and that edge should be a least cost edge. Okay, identify a least cost edge u comma v such that u belongs to TV and v does not belongs to TV. TV represents what? The vertex that were already visited. So identify an edge u comma v such that u is already in this list. Okay, but v is not in the list, right? Which means that v1 is in the visited list, but v2 is not in the visited list. So here we, instead of v1 v2, we are calling u comma v. U is in the visited list and v is not in the visited list. Okay. If there is no such edge, break. Otherwise, what you should do, add v to tv. Whatever the edge you have identified, if you have identified such an edge, then add this new vertex to tv and add this edge to t. Like this, continue. So there are the termination can happen either because of this or because of this. Because of this. Okay. So after coming out, or after coming out, you can display this TV content, which will contain n minus one edge. Suppose if it is not having n minus one edge, then you can say that there cannot be a spanning tree for this. Okay. Now let us apply for this understanding for this algorithm. Okay, for this graph. So initially, so let us call T. T is the set of edges. Initially it is empty. TV is the set of vertex which is visited. Initially it is 0, that is root vertex. So let us assume this is the root vertex. Now we have to identify an edge such a way that u is visited, v is not visited. So u is we have only 0 for u available. So from 0, if you see, there are two options, 0 to 1 and 0 to 2. So this is the only one option. So this is the one with the least cost. Okay, so we will add this edge, which edge 0 to 2. So now one more vertex is added, vertex 2. Now from this two vertex you have to consider. We have to identify an edge u comma v such that u is in the vertex list and v is not in the vertex list. So we have to consider 0 and 2. So from 0, if you see, we have only one option, 0 to 1, because 0 is added and 1 is not added. So this is one option. I will use a different color. Okay. So so far this is the only edge added. Okay. So now we have only, from 0 we have only one option, that is 0 to 1. We may consider this option. From 2, if you see, 2 to 3 is one option, because 2 is in the vertex list, 3 is not there. So 2 to 3 is one option. 2 to 4 is another option, because 2 is in the vertex list, 3 is not in the vertex list. So 2 to 4 is another option. 2 to 1 is another option, because 2 is in the vertex list, 1 is not in the vertex list. Now out of these 4, 0 to 1, 2 to 3, 2 to 4 and 2 to 1, we have to identify the minimum cost edge. Minimum cost edge is 2 to 1. So we will add 2 to 1 to the graph. So which edge we are going to add, in the sense we are going to add 2 to 1. So 2 to 1 we will add to the tree, spanning tree. This edge we have added. So now we have visited one more vertex 1. Okay. So this is the case at the end of second round. So now what we have to find, now again we have to identify an edge u comma v such a way that u is visited and v is not visited. But for u, the edge, the vertex which is visited. Now for u we have three options. What are the three options? 0, 2 and 1. For u we have three options, 0, 2 and 1. So from 0, if you see, if you see the edge which is not added, from 0 we have only from 0 we don't have anything, because 0 is added, 1 is also added. Okay, 1 is also added to the vertex list. So because what is the rule says, you have to identify an edge u comma v such that u is visited and v is not visited. So from 0, if you take this one option, 0 is also already visited, 1 is also already visited. 0 to 2, if you see, 0 is visited, 2 is already visited. So we don't have any option from 0. From 2, if you see, 2 to 3 is not visited. This is one option. 2 is visited, 3 is not visited. So this is one option. Okay. U should be visited, V should not be visited. 2 to 4, if you see, we can consider 2 is visited, 4 is not visited. So this is one option. Okay. Similarly, from 1, if you see, 1 is visited, 0 is also visited. So we cannot take this. 1 is visited, 2 is also visited. We cannot take this. 1 is visited, 5 is not visited. We can take this. So these are the three options. All the yellow colors are the three options. From this we have to pick up the minimum cost edge. Minimum cost edge is 1 to 5. So we will add 1 to 5 to the spanning tree. and we have visited one more vertex, that is 5. That is 5. Okay. So now in the next round, what should we do? So now the edge which is added is 1 comma 5. Now the edge that is added to the spanning tree is 1 comma 5. 1 comma 5. Now in the next round, what should we do? From all these 4 vertices, we have to identify such an u comma v such that u is visited and v is not visited. Okay. So from 0, if you see, there is nothing, already we know. 0 is visited, 1 is also visited. 0 is visited, 2 is also visited. So no option. From 2, if you see, 2 is visited, 1 is visited. So this we cannot take. We cannot take. 2 is visited, 3 is not visited. So still this option is available for us. 2 is visited, 3 is not visited. Similarly, 2 to 4, if you see, 2 is visited, 4 is not visited. So this option we have. Okay. From 1, if you see, 1 is visited, 0 is also visited. 1 is visited, 2 is also visited. So we don't have an option. 1 is visited, 5 is visited. So no option. From 5, if you see, we have only 5 to 1. 5 is visited, 1 is visited. So no option. So we have only 2 options. These 2. Out of these 2, which is the minimum cost edge? 2 to 4. So this is the one we will take. Which edge we will take? 2 to 4. 2 to 4. Okay. So 2 to 4. Now we have visited one more vertex, that is 4. Now we have visited one more vertex, that is 4. Okay. So now the edge that is added is 2 to 4. Now the edge that is added is 2 to 4. Okay. So this is the edge which is added to the spanning tree. Okay. Now for the next round, we have to consider all these 5 vertices, and we have to identify an edge u comma v such that u is visited, v is not visited. So now if you try, what will happen? From 0, there is no such edge. From 1, there is no such edge. From 2, there is one edge, 2 to 3. Because 2 is visited, 3 is not visited. Okay. Remaining, there is no other option from 2 also. From what else we have? From 1, there is no such edge. From 5, there is no such edge. From 4, there is no such edge, because there is only one edge, 4 to 2. 4 is visited and also 2 is visited. So there is only one option, we have 2 to 3. So this is the one which we have to add. There is no comparison also, because that is the only one edge we have. So now we add 3 to the vertex list. Now if you count the number of edges, we got the sufficient edge, 1, 2, 3, 4, 5, and the number of nodes or vertices were 6. So we got 5 edges, which means that already the spanning tree got created. Okay, already the spanning tree got created, and the recent edge which we have added is 2 to 3. So this edge also we have to add 2 to 3. 2 to 3. Okay. So this is the resultant spanning tree. Okay. If you try for one more round also, actually in the next round we will not be able to identify any edge. Okay, because in the next round already all vertices were added to TV. There is no edge which is not added. Okay. So from 0, all 0, what are the options? 2 and 1 both are available here. So you can't identify anything. From 2, we have 3, 4, 0 and 1. 3, 4, 0, 1, everything is here. So you can't identify. I mean, everything is visited. Okay. So you can't identify u comma v such that u is visited and v is not visited. No, every vertex is visited. So it will return null. So then that is also one of the way to stop the algorithm. Okay. Right. Now let us see the implementation of this. So here, this is the set of edges, and this is same as that of the previous case. I have not made any changes. And here all these are same. We have created one more array, visit, okay, which is used to represent whether a particular vertex is visited or not. Visit of 100, and there is a function initialize visit, where initially we ensure that visit of I, that I represents vertex number, visit of all vertex is 0. Initially none of the vertex are visited. Okay. And this is the function to check and to make sure that we are able to identify an edge such a way that the starting edge is visited. I mean, the starting edge is nothing but a starting vertex and ending vertex. Okay, so this is used to identify such an edge u comma v, such an edge u comma v, where u is visited and v is not visited. Okay, we have to identify such an edge where u is visited and v is not visited. So we pass some x where x represents the edge number. Okay, because the set of edges also we take as input. Then if visit of ed of x dot a, ed is an array which is an array of structures. So a represents the starting vertex of the edge. ed of x dot a is equal to 1 and ed of x dot b is equal to b 0. That is, visit of ed of x dot b is equal to 0. That means for this particular edge the starting vertex is visited and ending vertex is not visited. In that case we return 1 because we want to identify such a edge. Okay. Otherwise, suppose if you find this type of edge where starting vertex is not visited and ending vertex is visited, so that is also fine. Okay, because it is we are talking about undirected graph. So in that case, what we do, we swap the edges. We make the ending vertex as the starting one and the starting one as the ending one. We swap the edge and then we return 1. Okay. Otherwise, if this if none of these conditions, if both of these conditions were not satisfied, then we return 0. That means this particular edge, both the edges were either visited or both were not visited, like that. Okay, only that case it will fail. And this is the actual logic. Here we have made some changes. First we are asking the user to enter the number of vertices, then number of edges. Okay, then enter the all the edges and its weights. These are as usual in the earlier case. Then we are initializing the parent. Okay, where parent of I, for every vertex parent of I will be set as -1. Then we initialize visit, where visit of every vertex will be set as 0. Then we are displaying all the edges. Then we are asking the user what is the root vertex that we are taking. Then we are setting minimum weight some high number. So root vertex we are storing in a variable x. Then we are saying that visit of x is equal to 1. Because if you recall the algorithm, initially we assume that the first vertex is already visited. So here you see TV. TV represents set of vertex visited. So that is assigned to root vertex. Okay. So that we are writing this visit of x equal to 1. Then an infinite while loop, minimum weight set with high value. Then for all edges we check what edge. For I is equal to 0 to NED. NED represents number of edges. So for every edge we call this check of I. Check of 0 means check the 0th edge. What we want to check? Check the 0th edge means what? An edge is a combination of vertex, two vertex, right? Starting vertex and ending vertex. So we want to check what we want to check. We want to check whether in this edge one of the vertex, starting vertex is added to the tree and ending vertex is not added to the tree. That is what we want to check. For that we are calling this check of I function. So this check function, it will check what it will take just x, that is the edge number it takes, and then for that x it will take the starting vertex and its ending vertex, and that will be plugged into visit array. If starting vertex is 1 and ending vertex is 0, then it will return 1, which means that that is one of the edge which we are looking for. Okay, because starting edge should be in the visit list and ending should not be in the visit list. If it is other way, starting is not in the visit list, starting is 0 in the visit list, but ending is 1 in the visit list, that is also fine for us. So in that case we swap the edges and then we return 1. Okay, the swap logic is before it is same. Okay, so to swap a particular edge, what we say, previously whichever is A, whichever is B, now that will become A, and previously whichever is A, now that will become B. Okay, that is what it does. So after swapping we return 1. So in this for loop, first we check whether this is a type of edge which we are looking for. This for loop repeats for every edge. Then we check is this is a type of edge that we look for. What type of edge we are looking for? We are looking for an edge which is which is what such that u is already in the vertex list, but v is not in the vertex list. And if that is the case, then we check whether this edge is already added or not. If it is not added, then we check its weight. Is its weight is less than the currently identified minimum weight edge or not? If yes, then we say that minimum weight is equal to ed of I dot weight, and we note down this j. Okay, like that we do for all edges. Okay, but it will identify only such edge whose starting vertex is added and ending vertex is not added in every iteration. Okay, so and out of that it will identify the minimum cost edge. So that is what this for loop does. So this for loop actually ends here. So this will identify the minimum cost edge such a way that whose starting vertex is in the tree and ending vertex is not in the tree. Okay. Again, after coming out, we want to check whether if you add this edge, will it create a cycle or not. For this, we are calling this function x is equal to find out ed of j dot b, and y is equal to find out ed of, ed of x is equal to find out ed of j dot a, and y is equal to find out ed of j dot b. If x not equal to y, then it won't create a cycle. Then we say parent of y equal to x, and this is the edge which we are going to, this is the edge which we identified that we are displaying. And we say that ed of j dot added is equal to 1. One more edge added, and we update the total minimum cost. Okay. And then one more vertex also we have visited. So visit of ed of j dot b is equal to 1. Well, these things we do. Okay. Then we check if ne is equal to v. That is, if number of edges is equal to number of edge initially we set as 1. Okay. So if you start with 0, you can compare n is equal to v minus 1. As we are starting with 1, we are comparing if n is equal to v, then break. Okay. Previously we wrote this statement, but this is not required now because that is not the correct way of implementation. Right. So if n is equal to v, then it will break the while loop. Okay. So this is what the actual logic is. Okay. So let me execute it. So let me compile. PRIM underscore UP upgraded. Okay. So number of vertices, that graph we will take the second graph. Okay, this graph we will take. Number of vertices is 1, 2, 3, 4, 5, 6. Number of edges is also 6, I guess. 1, 2, 3, 4, 5, 6. Okay. Number of edges is also 6. What are the edges? 0 to 1 is one edge with a cost of 10. 0 to 2 is another edge with a cost of 7. 1 to 2 is another edge with a cost of 9. 1 to 5 is another edge with a cost of 5. 2 to 3 is another edge with a cost of 32. 2 to 4 is another edge with a cost of 23. These are the edges. 0 to 1 cost 10, 0 to 2 cost 7, 1 to 2 cost 9, 1 to 5 cost 5, 2 to 3 cost 32, 2 to 4 cost 23. Which is the root vertex? 0. So this is the edge it has identified. 0 to 2. Okay, so let us compare with our thing. So this is the first one, 0 to 2. Here, that's correct, right? 0 to 2. Okay. Next, 2 to 1. Next, 2 to 1. This one, 2 to 1. Okay. Next, 1 to 5. 1 to 5. Yes, 1 to 5. Next, 2 to 4. 2 to 4. This is 2 to 4. Okay. Next, 2 to 3. So this is 2 to 3. Right? Okay. So this is the resultant spanning tree. So the spanning tree will look something like this. This 2 edge will not be there. That is the difference. This 2 edge yeah, this 1 edge will not be there. Okay, this one edge will not be there. Okay, so totally it has 5 edges, right? Totally it has 5 edges. 0 to 2 is there. Yeah, 2 to 1 is there. Yes, 1 to 5 is there. 2 to 4 and 2 to 3. So this will be the result of spanning tree. Okay, so you can apply to other graph, the other one also, it should work. Okay, so that's it. So the principle behind here is initially set of edges which were added will be empty, null set. Okay, set of vertex will be the root vertex alone. Then in every iteration we identify such an edge u comma v such that u is already added to the vertex list and v is not added, and we identify the minimum cost edge out of that, and if it won't create a cycle we will add that edge to the edge list. Okay, so when you add the edge list, then the one of the vertex also will be updated, because you are adding u comma v. U is visited and v is not visited, so the v which is not visited, now it will be updated in the vertex list. Like that we do for every iteration until n minus 1 edges were added, or until you couldn't identify an edge such that u comma v where u is visited and v is not visited. Okay, so fine, let us stop here. Thank you.